In this video, we're going to discuss how gravity can shift the frequency of light in general relativity due to the presence of a spherical mass, described by the Schwarzschild metric. This frequency shift ends up being similar to the Doppler effect that we saw in special relativity in an earlier video. The method I'm going to use to derive gravitational frequency shift in this video uses the wave covector. You might find this method to be a lengthy and roundabout way of doing things. But my goal here is to show that the Doppler shift from Galilean relativity, Doppler shift from special relativity, and frequency shift due to gravity can all be handled using the same approach, for both inertial observers and non-inertial observers. We don't need to learn 6 different approaches and treat all of these as separate special cases. Just as we measure momentum and energy in different frames by measuring different components of the momentum vector in different reference frames, all we need to do to understand frequency shift is to draw the wave covector and then look at how different frames measure different components of the wave covector, and this will work every time in all cases. At the end of this video, I'll do a comparison between gravitational frequency shift in general relativity and Doppler shift in special relativity for non-inertial observers. And I'll talk about how these are related to the equivalence principle. In the Relativity 106A video, we saw that understanding the Doppler effect becomes very easy when we use a geometric object called a covector. As a reminder, a vector is like an arrow, and it represents something with a direction and a length. Meanwhile, a covector is like a stack, and it represents something with a direction and a density. Vectors are useful for giving geometric representations of things like position, velocity, acceleration, momentum, and force. And covectors are useful for giving geometric representations of waves, which have a direction and a density. A wave covector's density in time is the wave's frequency, and the covector's density in space is the wave's wave number. If we take a space-time diagram and imagine a wave traveling left over time, we can visualize the wave as a surface whose peaks travel left. We can then trace lines over the wave peaks to get our wave covector stack, which we'll call kappa. If we have a sound source creating a wave in space-time, we can measure the sound wave's frequency in different frames just by counting how many covector surfaces are pierced by a reference frame's unit-length basis vector. For example, Einstein's time basis vector pierces 2 wave fronts, so he observes a wave with a frequency of 2 Hz. But the car's time vector pierces 4 wave fronts, so it observes a frequency of 4 Hz. This is according to Galilean relativity, where we only tilt the time axis to change between inertial frames. For special relativity, we use the Lorentz transformation, which causes the time and space axes to move together like a pair of scissors. If Einstein observes this light wave to have one frequency, the car, which is running toward the light source, will pierce more wave fronts with its time basis vector, so it observes a higher frequency, meaning the light is blue-shifted. Similarly, if the car is running away from the light, its time basis vector pierces fewer wave fronts, and so it observes a lower frequency, meaning the light is red-shifted. From these geometric observations, it's easy to derive the formula for the relativistic Doppler shift of light, as we did in Relativity 106A. We even saw it was pretty easy to get the Doppler shift formula for an accelerated observer. In special relativity, accelerated observers travel along hyperbolic world lines, and each accelerated observer has their own Rindler coordinate system with coordinates ct tilde and x tilde. By comparing how many wavefronts are pierced by the hyperbolic world line's unit tangent vectors, we got an exponential Doppler shift formula for accelerated observers. So now let's see how covectors can help us understand the redshift and blueshift of light due to gravity in the curved spacetime around a spherically symmetric, non-rotating, uncharged mass, which is described by the Schwarzschild metric. As a reminder, in Relativity 108b, we derived the spacetime world lines of ingoing and outgoing light beams along the radial direction, with constant theta and phi coordinates. We just took a tangent vector d by d lambda and set its squared length to be 0, meaning it describes a light-like vector. Then we plugged in the Schwarzschild metric and solved the resulting differential equation to get these world lines for light. The world lines consist of a linear term and a log term. The positive solutions are for outgoing light beams, and the negative solutions are for ingoing light beams. Far away from the Schwarzschild radius Rs, the log term goes to 0, so the light beams just look like diagonal lines on our spacetime diagram. But close to the event horizon, the log term dominates, and the light beams appear to bunch up and go to infinity. We can also think of these curves as representing the wavefronts on a single ingoing or outgoing light beam, since as a light beam travels left or right, each of its individual wavefronts will follow a light-like trajectory. Unlike our last video on the Doppler effect, the wavefronts here are no longer positioned at a consistent angle. Their orientation changes depending on their location in spacetime. To describe these wavefronts, we need a Covector field instead of a single covector. To make a vector field, we just draw a bunch of vectors whose directions and lengths change depending on their location in spacetime. A covector field is the same thing, but with covectors. We just draw a bunch of covectors whose directions and densities change depending on their location in spacetime. But how do we know which directions and densities to use in order to describe a light wave? Well, remember, when a covector acts on a vector, the output is just the number of stack surfaces that the vector pierces. If a vector is parallel to the stack, the result is 0. So if we can get the tangent vectors for these light-like world lines, we just need to find the covector that's parallel to these tangent vectors, and acts on the tangent vectors to give 0. We can start with a tangent vector d by d lambda and expand it using multivariable chain rule over Ct and r. We're ignoring theta and phi since this is a radial light beam. Remember, partial derivatives of coordinate variables are just basis vectors. We can choose the path parameter lambda to be anything we want, so let's choose lambda equals r. Now, for our outgoing light formula, we see that dct by dr equals 1 over 1 minus rs over r, and dr over dr is just plus 1. So this is our tangent vector field for outgoing light beams. These components make sense, since they point up and to the right, which matches what we see on our spacetime diagram. As r goes to infinity, these vectors point at a 45-degree angle as expected. And as r approaches the Schwarzschild radius, the time term dominates and the vectors point almost completely upward. They also have a squared length of 0, as expected for light-like vectors. Now let's find a covector field kappa that eats this vector field and spits out 0. Remember, covectors are linear, so we can apply the covector to each term in the sum and then pull out the scaling constants. Kappa of ET is just the covector's time component kappa t, and kappa of ER is just the covector's radial component kappa r. Rearranging this equation, we find that a covector field representing an outgoing light beam will have a ratio of kappa r to kappa t that equals this. This is a covector field oriented to the upper left, which matches what we expect, as seen on our spacetime diagram. However, we solved for this ratio between kappa r and kappa t. It's still possible to scale both of them by some function alpha of t and r. while still maintaining the same ratio. So we don't yet have the complete solution for our light covector field yet. So how can we determine what this alpha function is? Well, first of all, since the Schwarzschild solution is static over time, we can assume that alpha only depends on r, and doesn't depend on time. And we can solve for alpha r by demanding that the covector field kappa has the property of being exact. As things stand now, we know the covectors in our covector field are oriented in the correct directions, because they act on light-like vectors to produce 0. So they are oriented parallel to light beams. What we don't know is whether or not we have the correct covector densities. If we have the incorrect densities, we could end up with a covector field where the stack surfaces don't join up properly. While this is a mathematical possibility, this doesn't make physical sense, since the lines in our covector field represent the wavefronts of a light beam, and the lines should all join up correctly. A covector field where all the lines join up properly is called exact. This is a covector field that can be generated by looking at the level sets of a scalar function. This here is an example of a covector field that's exact. It's basically the covector version of a conservative vector field, which is a vector field that can be written as the gradient of a scalar function. There are many ways to mathematically state a covector field is exact, but I'm just going to say our 2D covector field is exact if its curl is 0. So our condition for an exact covector field in space-time is that partial kappa r by partial time minus partial kappa t by partial r equals 0. Since kappa r doesn't depend on time, this goes to 0. So we're just left with the condition that the kappa t component, which equals alpha of r, has a 0 r derivative. This tells us that alpha of r must be a constant a. Plugging this in, we now have a covector field representing a light wave, with the correct orientations and densities. The constant factor a changes the density, but not the directions. So we were lucky that our covector field already had the correct densities up to a constant multiplicative factor. But we still needed to declare that the curl was 0 to be absolutely certain that the covector field was exact, the wavefronts joined up properly, and the densities were correct. We can also get another covector field for ingoing light beams just by using the ingoing light beam equations with the minus sign instead. Here, our tangent vector fields point to the upper left, and the corresponding covector field points to the upper right. Now that we have our covector fields for ingoing and outgoing light waves in Schwarzschild geometry, how can we use this to determine the redshift or blueshift of light due to gravity? You might be tempted just to take the covector field for light and apply it to the time basis vector to get the wave's frequency. This is almost correct, but remember, an observer makes actual physical measurements using an orthonormal reference frame, where each basis vector has a length of 1. This is because when measuring our covector field, we need to know how many wavefronts go by in 1 unit of time, so we need our time basis vector to have a length of 1. The time basis vector in Schwarzschild coordinates is not normalized to 1. Recall, the squared length of the ET basis vector is given by the GTT component of the metric, which is 1 minus rs over r. In order to normalize ET, we just divide it by the square root of 1 minus rs over r. This new time vector now has a length of 1. So we just put this new time vector into our wave covector and use linearity rules to pull everything out. Now remember, when an epsilon basis covector acts on a basis vector, when the two indices match, we get a 1, and when the two indices are different, we get 0. So we see that this light wave has a frequency of 1 over the square root of 1 minus rs over r times a. And technically, this is actually the frequency divided by the speed of light c. Just as we multiply the time coordinate t by c to get the same units as x, y, z, we need to divide the frequency by c to get consistent units with the x, y, z wave numbers. So this is the frequency of our light wave, and we see the frequency depends on r. So observers at different r positions will measure different frequencies for a single beam of light, depending on where they measure it. So gravity, which is the curvature of space-time around our mass, does change the frequency of light, depending on where you're observing the light from. If we make r go to infinity, this factor becomes 1, and we get a. So far away from the mass, this beam of light has a frequency of a times c hertz. As we get closer to the Schwarzschild radius, this same light beam will have a frequency that gets higher and higher, approaching infinity. What this means is that if we aim a light beam at a spherical mass, stationary observers arranged in a line will see the same light beam have a frequency that's larger and larger, the closer they are positioned to the event horizon. So an ingoing light beam from far away will appear to be blue-shifted to stationary observers close to the mass. It might seem strange that the frequency goes to infinity near the event horizon, but remember, a stationary observer near the event horizon has to apply a huge acceleration in order to maintain their constant position, and the acceleration approaches infinity as the constant position r approaches rs. Conversely, if a high-frequency light beam starting close to the mass is released outward, each constant position observer will see the same light beam have a lower and lower frequency the farther they are away from the Schwarzschild radius. The frequency changes according to the exact same r-dependent formula as the inward light beams, because the time component of the Covector field is the same in both cases. So for distant observers, the frequency is redshifted. As r goes to infinity, space-time becomes basically flat, and the light beam's frequency approaches a constant value of a. So this formula lets us compare the frequency observed at infinity and the frequency observed by a stationary observer at constant position r for a single light beam. But what if we wanted to compare the frequencies for two different stationary observers at constant positions r1 and r2? Well, we can just take their respective gravitational frequency shift formulas and then take their ratio. After some canceling and algebra, we see that this is the formula that determines how two observers at different constant positions near a mass measure the frequency of the same light beam. The last thing I'll do in this video is compare how gravitational frequency shift in curved spacetime compares to Doppler shift for accelerating observers in flat spacetime. The equivalence principle tells us that there is no difference between an observer in deep space in an accelerating rocket and an observer sitting on a planet's surface in a uniform gravitational field. However, the equivalence principle only applies locally. In mathematical terms, this means the curved spacetime of general relativity can be approximated by the flat spacetime of special relativity that is tangent to the curved spacetime at a given point. But as we move away from this point, special relativity becomes a worse and worse approximation of general relativity. So if someone is standing on a planet with the molecular forces of the planet's surface forcing them upward, away from a geodesic, this person's foreacceleration vector would point upward. Locally, this is equivalent to someone in deep space being inside an accelerating rocket. This person's foreacceleration vector would also point upward. So locally, these two situations are equivalent. However, non-locally, these two situations are not equivalent. The gravitational effects on a series of rockets hovering above a planet in curved space-time are not equivalent to a series of accelerating spaceships in deep space in flat space-time. So when examining frequency shift effects non-locally, gravitational frequency shift seen near a planet is not equivalent to the Doppler frequency shift we see in accelerating spaceships. In the Relativity 105b video, we learned that accelerating spaceships in special relativity have hyperbolic world lines. If two spaceships accelerate so that they have the same proper acceleration readings on their accelerometers, in their own frames, they will get farther and farther apart. In order to maintain constant distances along a line of accelerating spaceships, as measured in their own frames, each ship must accelerate according to this formula, inversely proportional to its x tilde position. Each spaceship will travel along a hyperbolic world line, but each hyperbola will get less and less curved in the direction of acceleration. Previously, we measured these hyperbolas using the x tilde position coordinate and the ct tilde time coordinate, which acts as a hyperbolic angle. However, we can redraw this space-time diagram in such a way that the Rindler coordinates ct tilde and x tilde form a grid, and the hyperbolas become vertical lines. In this coordinate system, we measure space-time intervals using the Rindler metric. The Rindler metric tells us about the time dilation experienced by these spaceships. It says that proper time is proportional to the x tilde coordinate. So this means that 1 second on the first spaceship corresponds to 5 seconds on the fifth spaceship, if we're measuring along this line of simultaneity here. Now, how does this compare to the case of a line of spaceships firing their rockets above a planet so that each one maintains a constant height above the planet? Because the spaceships are firing their rockets to hold their positions, they will each measure a proper acceleration on their personal accelerometers. According to Newtonian gravity, each ship would measure a value of gm over r squared on their accelerometer, where m is the mass of the planet. However, if we calculate the proper acceleration according to general relativity, we get the same result, but multiplied by this factor, which drives the proper acceleration to infinity near the Schwarzschild radius. However, since the Schwarzschild radius Rs is very small for most planets and stars, this is approximately equal to the Newtonian result. In either case, note that the accelerometer readings change with 1 over position squared. We also saw in Relativity 108b that the Schwarzschild metric results in gravitational time dilation according to this formula. So, the case of accelerating spaceships in deep space and the case of spaceships hovering above a planet do have similarities. In both cases, the ships all measure proper accelerations that are decreasing in the direction of acceleration. And in both cases, the ships experience time dilation, with time passing more quickly in the direction of acceleration. However, the two cases are not globally equivalent. The ships in deep space have a proper acceleration formula that changes with 1 over position, and the ships above the planet have a proper acceleration formula that changes with 1 over position squared. They also have different time dilation formulas. Going back to frequency shift, the frequency shift effect in both cases is similar, with a beam of light being blue shifted according to observers on the left, and the same beam of light being more red shifted according to observers on the right. However, the formulas for frequency shift are not equivalent. Again, one falls off with 1 over position, and the other changes with this square root formula. So, while an accelerating spaceship in deep space is locally equivalent to standing on a planet, or firing your rockets to maintain a constant position above a planet, globally, the two cases measure different proper accelerations, different time dilations, and different frequency shifts. so we cannot treat gravitational frequency shift and Doppler frequency shift as globally equivalent. Also, if you want to know where these formulas come from, you can pause and look at these derivations. For proper acceleration of a stationary body in Schwarzschild geometry, we use the fact that the length of an observer's four-velocity vector is c to derive the ut component. Then we compute the four-acceleration using the covariant derivative of u in the direction of u, plug in the connection coefficient, solve for the four-acceleration vector, and then find its length to get the proper acceleration. For the Doppler shift for accelerating spaceships, we can show the paths of light in Rindler coordinates obey an exponential formula. Then we can calculate the light-like tangent vectors d by d lambda, then get a light Covector field by forcing the covector to be parallel to the light-like tangent vectors, and forcing its curl to be 0 so that the densities are consistent. Then we normalize the time basis vector and apply the Covector field to it to get the formula for the frequency of a light beam as a function of position. So to summarize this video, since a covector is a stack of surfaces, we can put a covector at every point in space-time to get a Covector field. The wave fronts of a light beam in space-time can be represented by a Covector field, where the covector densities across time represent the light wave's frequency, and the covector densities across space represent the light's wave number. We calculated the Covector field for a radial light beam in Schwarzschild geometry to be equal to this, where A times c is the frequency value very far away from the mass in flat space-time. By applying this Covector field to a time basis vector with a length of 1, we were able to determine that an observer at a constant position r measures the light to have this frequency. Basically, the same light beam is measured to have a more redshifted frequency by stationary observers far from the mass, and is measured to have a more blueshifted frequency by stationary observers closer to the mass. We also compared the cases of accelerating spaceships in deep space and the accelerating spaceships above a spherical mass. Although frequency shift is observed in both cases, the frequency shift in each case is different because accelerating in flat space-time is globally different than maintaining a constant position above a spherical mass in curved space-time. Remember, light waves have no objective frequency value. To get a light beam's frequency for a specific observer, we need to grab that observer's unit length time basis vector, which represents 1 unit of time in their reference frame, and count how many wave peaks are observed across that 1 unit of time. This general approach allows us to understand frequency shift in all cases and in all reference frames.